Hopefully you recognize some patterns when you were working through the problems in our last lesson that will help you make sense of the exponent shortcuts that we're going to take a look at in lesson 6.3. Remember that exponents represent repeated multiplication or repeated division. So if I look at the first example, I could think about this the way we did in the last lesson and list out all the factors of A. So I have a factor of A, another factor of A, and then 4 factors of A. They're all multiplied together. So in all, I have 6 factors of A, or A raised to the 6th power. Now let's look at an easier way to get to that result. If I have a factor of A, then the power on that is a power of 1. We don't usually write the 1. So my next factor of A also has a power of 1. So if I want to know how many factors of A I have altogether, I can just add the exponents. A to the 1st power plus another A to the 1st power plus an A to the 4th power. And if I add those exponents, you see that I get A to the 6th. So that's our shortcut. As long as we have the same base and we're multiplying, we can add the exponents together. So when I see a problem like D to the 3rd power multiplied by D to the 9th power, instead of listing them all out, I can just raise D to the 3 plus 9 and then simplify that sum, D to the 12th power. Now it only works if you're multiplying and if your bases are the same. So in example C, you see that we have more than one letter. But we can rearrange the multiplication because we can multiply in any order. You don't have to actually write this down. You could visualize it, but I'm going to go ahead and write them together. I'm going to put my G factors together, G to the 0 power times G to the negative 7 power times H to the negative 1 power times H. And since that H doesn't have a power, we understand it to be H to the 1st power. So now it's easier for me to see that I have the same base and they're multiplied, and that means that I can add the exponents. So G to the 0 plus negative 7, and then H to the negative 1 plus 1. And those are still multiplied together. 0 plus negative 7 is just negative 7. So G to the negative 7 power, and then H to the negative 1 plus 1 is 0, and any number to the 0 power is just going to be 1. So I can write times 1, but to simplify that, when I multiply by 1, I just leave it off, G to the negative 7. This shortcut works on rational or fraction exponents as well, and is really required for that because it would be really hard for us to write out r to the negative 5/2 power. But since we have the same base and they're multiplied, we now know that we can use this shortcut of r to the negative 5/2 plus negative 3/2. Just add those powers together. Now if your fractions have a common denominator, then they're easy to add together without a calculator. But if they don't have a common denominator, or if you just want to type it in your calculator, feel free to do that. If I have negative 5/2 and I add negative 3/2 to that, that gives me a total of negative 8/2, and I can simplify that to negative 4. What about r to the 2nd power plus r to the 3rd power? Can we apply our shortcut to that? Because we have the same base, but they are not multiplied, right? They're added together. And this only works if we're using multiplication, because exponents represent repeated multiplication. So this cannot be simplified using our exponent shortcuts. Next, let's look at a shortcut when we are dividing and we have the same base. So our first example is b to the 4th power divided by b to the 3rd power. In our last lesson, what we did again was we wrote out how many factors of b we had in the numerator and how many factors of b we had in the denominator. And then we said, well, if we have the same thing on top and the bottom, then that cancels out because it's a factor of 1. So we would cancel those and cancel those and cancel those, and it would leave us b to the 1st power on top. But if we have fractions for our exponents, or if our exponents are very large, then it's not practical to list them out like that. So we need another way to look at it. But really what we're doing is subtracting the number of factors that we have on the bottom from the number of factors that we have on the top. So we can, when we're dividing and we have the same base, we can subtract the exponents. We can call this b to the 4th power minus the 3rd power. It's always the top exponent minus the bottom exponent, even if that gives you a negative exponent. So b to the 4 minus 3 is equal to b to the first power. We can see that's what was left over when we listed those out. Let's apply that shortcut to our next example. We have 8 factors of u in the numerator, and we have negative 5 factors of u in the denominator, so we can simplify by subtracting the exponents. We're going to take the 8 that's the top exponent, and we're going to subtract the negative 5 that's the bottom exponent. Now if you're subtracting a negative, that's the same as adding, so this is really u to the 8 plus 5, which is 13. In our next example, we have lots of different bases, but they're all multiplied together, and we can separate them out and reorder them as we need to in the numerator or the denominator, and think of them as separate little fractions. Since there's no addition or subtraction, we can multiply these in any order. So I'm going to rewrite these as smaller fractions, t over t multiplied by u to the negative 1 over u to the negative 1, multiplied by v to the 0 over v to the 0, and multiplied by w to the negative 1 divided by w to the 0 power. Now there are lots of ways that you could use the rules for exponents to simplify these little fractions. I noticed that for 3 of these 4 fractions, I have exactly the same thing on the top and the bottom of the fraction, which means that those fractions are equal to 1. So the easiest way to do this would be to cancel out those as factors of 1. However, we're looking at the division rule when we have the same base, so I'm going to use that rule instead. So if I have t to the first power over t to the first power and I subtract the exponents, I get t to the 1 minus 1. 1 minus 1 is 0, and t to the 0 power is going to be 1. We're assuming here that none of these bases are equal to 0 or 1. So in the next little fraction, I have u to the negative 1 over u to the negative 1. If I subtract those exponents, u to the negative 1 minus negative 1 is going to be negative 1 plus 1, which is u to the 0, which is also simplifying to 1. V to the 0 power is 1 over v to the 0 power is 1, so 1 over 1 is 1. And then finally I have w to the negative 1 power divided by w to the 0, and I can subtract those powers. Negative 1 minus 0 is just negative 1. So when I multiply by 1, nothing changes, and I'm left with just w to the negative 1. And finally, let's look at an example where we have division with the same base, but our exponents are fractions. Our rule remains the same. As long as our bases are the same and we're dividing, we can subtract the exponents. So r to the 17 over 6 minus 1 over 6, those have a common denominator, so that's easy to do the subtraction. 17 minus 1 is 16 divided by 6, and then I need to reduce that fraction. Now my exponent's getting a little bit big right there, the way I've written it, but remember that it should be written in the air. I'm going to rewrite it here. If I divide 16 by 2, then I get 8, and if I divide 6 by 2, I get 3. So r to the 8 thirds is our final answer. And the last shortcut we're going to look at is when we have a single base, but it's raised to 2 powers. So the way we did that in our last lesson, if we saw something like 8 to the 9th power raised to the 2nd power, we said, well, that's 2 factors of x to the 9th. So x to the 9th multiplied by x to the 9th. Now we could use our shortcut for multiplying when we have the same base, and we could add those exponents, x to the 9 plus 9. But 9 plus 9, another way to write that is 2 times 9. And we could have gotten there from the beginning by just multiplying those exponents together. So that's the shortcut. X to the 18th power would be our final answer. So when we go to example B, we're just going to multiply those exponents together. T to the negative 3 raised to the negative 10 is just t to the negative 3 times negative 10, which simplifies to t to the 30th power. So we're multiplying these exponents when we have a single base raised to 2 powers. And that's different from our first shortcut where we had 2 bases that were multiplied together and we were adding the exponents together. Look at example C. We have a product in parentheses. Product means we're multiplying things together. So all these things are multiplied together and raised to the second power. When you get a pattern like that, you're going to raise every factor in the group to that power. So I'm going to have w to the negative 9 multiplied by 2. I'm going to have x to the negative 9 multiplied by 2. And I'm going to have y to the negative 6 multiplied by 2. So each of the factors on the inside gets raised to that power. If I simplify, w negative 18, x negative 18, y to the negative 12. In example D, we have a number factor, 4 is a factor, and c to the 9th power is a factor. They're grouped together and both raised to the 3/2 power. So our shortcut remains the same. We're going to take our number 4 and raise it to the 3/2 power. We're going to take c to the 9th and raise it to the 3/2 power. So that means we're multiplying those exponents together. Now I can think of that 4 as being to the 4th power or to the 1st power. And then if I multiply 1 times 3/2, it's just going to give me 3/2. So I usually don't write the 1. I just take the power to that number or to that first factor. Now remember how we simplified a fractional exponent on a number? We took that base and we said, look at the denominator, I need 2 factors, same factor, multiplied by itself to equal 4. And so we know that's going to be 2 times 2. And then if I look at the numerator, it's 3. That means I need 3 factors of 2 to simplify this. So 2 to the 3rd power. And then on the c, I can just multiply 9 times 3/2, which is 27/2. 2 to the 3rd power is 8. So this is 8 to the 27/2 power. In the next example, I have 3 factors in the parentheses. I have a factor of 2, I have a factor of w, and I have a factor of x to the 1/2 power. So that fractional exponent is on the inside of the parentheses, and it only affects the x. The 6 that's an exponent on the outside of the parentheses affects every factor that's on the inside of the group. So I need to raise 2 to the 6th power. I need to raise w to the 6th power, and then 1/2 to the 6th power, or x to the 1/2 to the 6th power, is going to require me to multiply those powers together. 2 to the 6th power is 64, and then w to the 6th power, and then x to the 1/2 times 6 is 3. So if you ever get fractions that you're unsure about how to multiply them together, you can use your calculator to do that. Here's one more thing to look out for. This expression, the group 4 plus x squared raised to the 3rd power, looks similar to what we've been doing, but notice that plus sign that's inside the group. On all of our examples up here, when we had something raised to a power, everything inside of a group was a group of factors or things multiplied together. Once there's a plus sign or a minus sign inside of our group or between our variables, then it doesn't fit the structure that works for our exponent rules. So remember that exponents are repeated multiplication or repeated division, and so addition or subtraction will not work with these rules. So we just need to leave this one alone. Be sure and do your practice and then take your mastery check. Let me know if you have any questions.